Hi, so I'll just give a brief introduction. Professor Preindl completed his bachelor's and PhD at the University of Padua in Italy and his master's at ETH Zurich. He's been a professor in electrical engineering at Columbia since 2016, where his research focuses on power electronics for a number of applications. He's made a number of notable contributions, and today we're delighted to host him for his talk on a subset of these contributions, which is titled Software-Defined Power Electronics for Grid Interactive Electric Vehicles. Okay, wonderful. Do you want to take it from here?
Thank you for the introduction, and thank you for hosting me. I'll start maybe with a bit of providing a bit of context. My laboratory is started about 5 years ago at Columbia University. We started to introduce power as a topic of focus at the electric engineering department, and we focus mainly on motor drives, power electronics leveraging controls, in particular for power electronic systems, with applications in motor drive systems, but then also we leverage it for vehicle charging, but also battery management. Much of in today's discussions, I'm going to show some of our work in the context of software-defined power conversion. That's a concept that leverages high-performance power electronic modules. So we could think about it as Lego-like building blocks, if we will, that are then aggregated by control and software to form functional power converters like three-phase inverters or single-phase DC-DC converters, and so on. The starting point for much of our work is global warming, CO2 emissions, and so on. So we tend to focus on systems that benefit renewable energy. We know that we have a finite CO2 budget, and we are, at least at the moment, not on a trajectory of meeting or staying within the bounds of the CO2 budget that we have. The core application that we leverage is electrified transportation. We know electric vehicles use a number of power electronic converters, ranging from onboard and offboard battery chargers. Vehicles need inverters to drive their traction motors, which, depending on the vehicle, it's a single traction motor, or it's a motor per wheel, or it's a four-wheel drive system. And then there are certain battery management hardware that is needed to balance the battery levels. So high voltage batteries consist of multiple battery levels, and we need some, at least circuitry, power circuitry that manages and balances those batteries. So there are DOE targets for each of these subcomponents in vehicles, and one of the thoughts that we have is that, we could attempt to optimize each of these smaller systems, or we could potentially try to integrate multiple systems into one system and try to find an optimum over, let's say, a larger boundary. And we know that in general, global optima tend to be better than the sum of the individual local optima. Some ideas or some work that we did in the past is vehicle battery management systems. We focus on, or we implement machine learning algorithms for batteries, but then we also focus on traction motors, integrate charging. This is an example that I will make today. and then we use battery charging. And one of the concepts that we have been looking at is what we call transformerless battery charging. And that's another example that I will make today. So I'd like to start to discuss what we mean by software-defined power converter. And what we mean is we start building small power converter blocks. They're related to what what is known as power electronic building blocks, only that these converter modules, they resolve locally all power electronic challenges. So what that means is that each module has power electronics, has a filter locally, and it has a controller that actuates a desired behavior. These modules are connected by a real-time bus system, and then tied together, and then a higher level controller defines what the functionality is. And these can be, so a simple example would be that each of these power converters is a phase leg of a three-phase converter, and then the higher level controller performs the multi-phase or three-phase control action, which may be the control of a DC bus or the actuation of a torque to a motor or something along these lines. To abstract the concept a bit and maybe to explain the different layers needed to implement a system of this type, is we have defined 3 layers. And the layers that we describe is we have at the lowest level, we have a generalized module layer. So each of these lowest level modules, they can act as voltage source, as a current source, or also potentially as a resistor if that's a behavior we want to have. And then each sources for controlled current sources, and they receive the input of a higher current layer to make them behave in the intended way. And that is communicated through a layer, and that software-defined layer that is aware of the generalized application, which is the even higher layer, and that is the application function layer. So the function layer is, well, are we in the context of a wind turbine? Is this a bigger like EV battery or a single three-phase grid and so on? And then from both sides, there are abstractions, and we can use generalized libraries to tie the component and things together. We can, so at the lowest level, I mentioned that, so we use always the same power conversion module, but we can operate it in different ways. So we can make it behave as a voltage source, or we can make it behave as a current source, and they have different uses for different applications. Similarly, at the higher level, we have generalized application function blocks, which is, for us, we call this a library that uses standardized things like phase lock loops, speed control, torque control for a motor, general transformations, battery charging control, and so on. And then the middle layer ties these things together and essentially wires up the different layers together, and make sure that the intended control action is applied by the correct physical hardware module to the system. 2 examples One is a three-phase grid type converter. So this is a three-phase converter connected to the electric grid, which is a typical example that I will keep making. So we have a higher level controller in the application function layer. So this is a very off-the-shelf controller that controls the grid current. And we have the reference frame transformations from the phase reference to the DQ0 reference and back. And then each of these values, so essentially what usually be sent to like a duty cycle is now sent to a pulse width module, is now sent to each of these modules, and each of the modules has its own local controller that then actuates it to its output. And on the right-hand side, that's an example, a code screenshot that shows how this system behaves. Similarly, same hardware reprogrammed. Now we have a higher level. So the lower level is the exact same system, same modules, everything. Now the application was switched out from the grid to a permanent magnet machine. And now the application layer now uses a speed controller. So now we use the necessary transformations again. And now the machine, instead of actuating a certain current, we actuate an intended torque. So we want to slow the machine down from a certain speed to the negative speed. And we actuate the torque according to the limits of the machine and so on. Keith, do you allow questions during the talk, or should we wait for the end?
We do. Usually we wait till the end and we do the questions off recording.
Okay.
But if anyone has questions, just raise your hand and you're welcome to chime in. But otherwise, we'll just save them for after, Matthias.
Sounds good. Either way is perfectly fine. If there are questions, you're welcome to ask. Next up, so this is the highest level. So now we are looking more at the modules. So how do these, let's say, these building blocks or these Lego blocks look like? And while to make this system even remotely, competitive or even meaningful, we need high performance modules. So they need to have very high efficiency. Just to give a number, 98, 99% would be is needed to make sense, such that this system makes sense. And then they need to have high performance, high control performance. Each of these modules has inductors and capacitors, so there's a potential for oscillation. So there's a need to damp some of that. And then we need to control them. So we started by leveraging what we call critical soft switching that we apply to an H-bridge. So what we do is we start to decrease. Let me find the correct slide. So what we do is we try to mitigate the turn-on losses, which tend to be about a factor 3 to 5 higher than the turn-off losses in well-designed MOSFETs. And what we're doing is, so in MOSFETs, we have two types of switching transients, while the turn-off and the turn-on. During the turn-off, we have we actually have the capacitance, these parasitic output capacitances of the MOSFET clamping the voltage during the switching transient to 0. So the output MOSFET, the output capacitance actually helps to have what we call 0 voltage transition. During the turn on, the reverse happens. During the turn on, we have a current, or the diode, the upper diode in the example turns on, and what we'll see is that now when the MOSFET switches, we are now shorting the capacitors into the switches. And what that means is that we're essentially increasing the switching losses. But we can attempt to try to mitigate the turn-on losses. And one way we can do that is that we start to increase the switching frequency. So to give an example, so hard switching, we have the peak of the current and the minimum of the current. They're both positive. For soft switching, we would need to have the minimum to be negative. And depending on the switch, the turn-on losses can be by far the dominant loss component. And so that was the case also for our switches, at least. So we introduced critical soft switching. Increasing this limit, we can draw a line, a boundary. So where we have a soft switching region, so we need to limit the, so there's a trade-off between the currents that we can allow and the time that is necessary, so the dead time that is needed for the transition. There is a cross dependence, but we can force soft switching in the switches by increasing the ripple. This can be done in DC operation and AC operation. We need to manipulate the current ripple. And what it means is that the minimum needs to be negative and the maximum needs to be positive. So if the average current in DC increases, we need now to increase the ripple as well. And the minimum needs to stay constant. Or in an AC case, if we have an average output current, we need to increase the switching in a way that the peak, increases and the minimum stays always negative and the positive stays always positive. In sinusoidal, this means that we essentially have a continuous time variation of the switching. And that can be tricky because we have potentially out of sync behavior of our sampling of our switching behavior. So in general, it makes things easier if we can change the switching frequency according to periodic intervals. So instead of having a continuous time variation, we have a discrete time one. And that gives us, so instead of the continuous time critical soft switching, we get the discrete time version that now has steps in the switching frequency behavior. And that's shown on the lower right of the screen. Some examples, so in the system that results from this design, it tends to move or change the switching frequency significantly. Currently, we go up to 1.2 megahertz with silicon carbide. That's at the 22 kilowatt level. And what happens is the switching frequency is always changing. This is the continuous time version. The grid current is sinusoidal, as you would expect. However, the inductor current that behaves exactly or follows exactly the intended shapes, and that means the minimum and the maximums. One is always negative, one is positive. The switching frequency also depends on the output, because if the current magnitude is smaller, we don't need to allow too high of a ripple, and as a result, we can maintain a higher switching frequency. The reason why we can maintain a higher switching frequency, it's soft switching, so the losses tend to be low. But there's a secondary effect, and that is that if you allow high ripple, then the magnetic, so there will be losses in the copper, in the coil, copper losses, and core losses in the inductor. So there's a trade-off between switching fast and generating losses in in the inductor. The second example is the discrete time switching. So now we have a step function for the individual switching frequencies. The output current looks pretty much the same. We are now, the only difference is that now we're not changing the switching frequency continuously, but we're stepping it down in discrete intervals. And that is seen in the inductor current, but it doesn't really have an effect on the capacitor voltage or the grid current. In general, the discrete time frequency is the switching frequency is lower compared to the, so it's always a lower bound to the continuous time variable frequency, and as a result, we always have a higher ripple. Skip that. Combined with the varying switching frequency, we can also optimize, or we need to optimize the design. So we said that by choosing capacitor or varying the switching frequency, we can also introduce a large ripple, and we also obtain so we introduce a large ripple, which we need to mitigate the resulting effect of the large ripple on magnetic losses. So there are two ways we can do that. One is we can try to make the inductor as small as possible and potentially increase the frequencies even higher. And one way that we leverage is that we are increasing artificially the output capacitance of the switches. So the top waveform is the switching behavior from one to the other, from turn on to turn off. So this is a turn off transient without additional capacitance, so external capacitance. We can add 150 picofarad or 300 picofarad, and what you would see is that the overall loss energy, the switching loss energy, it goes down, but the switching transient becomes larger. So there is a limit of external capacitance that we can add, because eventually we limit ourselves in how fast we can switch. But until there, we can start at or continue at switching our external capacitance to limit the losses. The second, and perhaps more important, is we need to design a magnetic inductors that can deal with these high switching ripples. And that means, in general, to oversize the cores and to use coils that have sufficient litzes and high frequency behavior to mitigate losses. These are three inductors. One is a 20 kilohertz hard switching inductor. Then we have a variable frequency 40 to 160 kilohertz variable frequency soft switching inductor, and then we have a 100 kilohertz to 1 megahertz variable frequency inductor. And between the three, the last one is about 1/4 of the size of the second to last, and the first one is significantly bigger, as the picture might suggest. As a result, so just by observing this, is that the critic soft switching allows us to reduce the inductance by a factor of 5 to 20 with the same switches. Now, we are also investigating alternative designs, which means that we implement essentially Litz wire configuration into PCBs, and we try to transpose individual layers to mitigate skin effect and proximity effect. And for some areas that is doable. It is possible to mitigate some of these effects. However, for beyond a certain frequency, Litz wires are better, or for even higher frequencies, plain PCB wires tend to be still better because they have less. We have a better DC resistance. As a overall explanation of the hardware implementation, so this is an implementation with three what we call autoconverter modules. Each of them has its phase lag, LCL filter, and we can, through this design procedure that I just outlined of combining or using variable frequency critical soft switching, combining it with optimizing the inductor and optimizing or adding output capacitance to improve the switching behavior. It's possible to draw this red line, which is essentially the boundary of the design methodology. And the prototype that's realized on the right-hand side, that's the green dot that's realized here. And it achieves about 10 kilowatt per liter and more than 99% efficiency. The other blue dots here, these are existing converter designs that have been published in literature with the very high power density one. I believe that's a gallium nitride design, if memory serves well. This is the hardware component. The last bit for the lowest level that we need is a local controller. And the main goal of that controller is to make each individual module to behave according to our target. And that is, we have now some switches and some inductor capacitors, and we want to make them behave as a voltage source or current source. And the way we are thinking about this is that we have a module that we want to potentially make cheap-ish. So we don't want to use too many sensors, and we want some high-performance control to maximize bandwidth. So we are leveraging locally state estimation, specifically receding horizon estimation. And for the control, we use predictive control. So for both cases, we are essentially write or describe the module in a state space system, and we start estimating parameters and we start estimate currents and voltages in the module, and then have a prediction of voltages or intended behavior. Typically, that's the output voltage, and we provide a sequence of that to the module, and then the module actuates that to the system, actuates that. I skipped the design procedure for the control. One good behavior or one interesting behavior of this type of module or MPC implementation is that they inherently dampen behavior. So if I design a controller that knows that there are inductors and capacitors, then these controllers, they inherently dampen out resonances. So there's no need for some of the conventional approaches like notch filters or similar approaches that are popular in vector control. So what we can do is we just implement an MPC controller, and then we can actually start almost arbitrarily stack modules or put them in parallel and or series. And even if there are LC components in the system, the system is controlled, and therefore the individual components behave quite well. That of course is as long as the LC resonances are within the control bandwidths and so on. Maybe the last note is that I talked about three-phase components, so each of them are essentially single-phase equivalent circuits. They are just implemented as three phases per PCB to simplify testing on our end. But one thing that these systems have is they inherently stabilize the common mode or the zero sequence, and that is a property that has become quite of interest to us, and we have started to leverage it in several designs. And the benefit is, again, we can start parallelize inverter modules, inverter phases, which is conventionally hard to do. And one component or one way how this is of particular interest to us is we are leveraging in for transformerless battery charging applications for vehicles. What it means to remove or to have this a stabilized zero or common mode voltage is, you can see at the right-hand side there is like a table with the leakage current for a non-isolated inverter, and with this system we are below 15 milliamp, which is typically a limit required by grid standards. And if we don't stabilize the common mode, then we have the common mode voltage that's jumping up and down by half of the DC voltage. And what we obtain is a factor, more than a factor of 10 higher, actually factor of 500 higher current, a factor of 50, apologies, factor of 50 higher leakage current to ground. And those are definitely outside of the common grid requirements. So I'll make two examples how we use this type of systems. One is to implement electric vehicle charging equipment. Conventionally, to implement a vehicle charger, we have a battery that has some leakage capacitor. So every system, be it a photovoltaic panel or a battery, they have parasitic capacitances to ground. In a vehicle, that's the chassis. During charging, the vehicle chassis needs to be set to ground in case there is a fault. So there is a potential ground loop between the grid and the battery. This is the same behavior that happens in photovoltaic as well. And if we don't manage this ground loop, we can get potentially quite high leakage currents to ground. Because the switches switch fast, and so even a small parasitic capacitance to ground provides a suitable conduction path. A common approach today is to simply put an isolation transformer, a high-frequency isolation stage between the grid and the battery. That's one way to go about it. One of the challenges is that for unidirectional designs, that works quite well. Typically, the efficiency is in the 94 to 97% today, perhaps a bit higher. However, if we try to make these systems bidirectional, now we need a lot of switches. And one of the challenges is to keep or to achieve a suitable cost. The way we are thinking about is to introduce or to combine 6 or multiples of 6 phase legs together and form what we call a transformerless charger. They are fully balanced and stabilize the common mode, so the leakage remains below significant below the threshold, and this conduction path or this path reduces the leakage current by 90%. There are some examples. So the upper one was the first prototype that was very slow switching. Then we have completed version 2 about a year and a half ago. And we are now working on version 3, which is about 1/5 of the size of version 2. The efficiency, so you can see there's an example of the charging behavior. These are experimental measurements, actually. So there's constant voltage, constant current charging for the to charge a battery, and the efficiency ranges from well, at the lower end, lower voltage and lower power end, from the 95-96% up to the 99% plus at the higher power levels. The EMI and standards compliance is important. Typically, there are two standards we need to manage when we talk about grid-connected converters. One is the harmonics, up to about harmonic number 50, so 50 times the grid frequency. And then we have the high-frequency components, EMI. And so for the harmonics, so the red are the measured harmonics, the blue are the allowed harmonics by standards. So this is essentially, these are the experimental measurements. And similarly, we have the EMI measurements. So we need to essentially stay below certain limits outlined by the standards. Similar for the common mode leakages. This system, so if you have many building blocks, many power electronics building blocks, this is inherently a bidirectional system, or we could move pretty much any power to any output node. So while we implement rather conventional controls that work on top of the individual power building blocks, and so the one side behaves as a DC-DC converter, one side behaves as a DC-AC converter. And then even on top of that, we built a typical grid controls. So vehicle-to-grid is becoming an interesting or a relevant topic since it can sustain the electric grid significantly. And one or some of the services that are provided or can be provided by vehicles are aligned with the services that can be provided by solar inverters, which are specified in IEEE 1547. And these are essentially reactive power control. We can have a constant reactive power control, constant power factor control, or also dynamic control. So these are controls that it's the mode of the inverter or the vehicle charger that it's put in where the in standalone, the local controller reacts on frequency variations or power variations or voltage variations and tries to stabilize frequency or the local voltage and so on. And these are already outlined in existing standards. And there are different modes that these converters can be set to and are executed locally. The part that's currently still worked on, and I think that there's quite some, the people are still trying to standardize around, is how do we communicate with individual chargers, for example, such that they become interactive and they can react based on a central control signal. So this is the vehicle charger example. We also integrated this type of inverters in a motor drive, well, in a scaled motor drive. And so now we are using these power electronic building blocks to drive a motor. But then if we don't drive, and well, it seems obvious that we tend to not drive the car while we charge it. We can use the same hardware to charge, fast charge, or slow charge, or DC charge our battery. And what we can do is, so we can use the same hardware again. It's just a matter of reconfiguration, and we are defining our functionality by software anyway. So this seems to be a reasonable application. What we initially thought is that adding filters, so LCL filters between the charger or between a three-phase inverter and electric motor might not be a good idea. It might degrade efficiency. However, it turns out that the switching losses or the switching behavior of an inverter, if unfiltered, it tends to drive significant iron losses in electric machines. And as a result, it turns out that doing a reasonable soft switching with LC filter and mitigate some of these losses, dedicated filters tend to be better at absorbing losses than electric motors that primarily use electric steel as compared to high frequency ferrite. So it's actually possible to improve drivetrain efficiency by introducing filtering, which not by much, but we are estimating about 0.5% to 1% in typical implementations, which can be a lot. And then for charging, we did some tests, and the efficiencies that were achieved are exceeding 99%. This is a system that's designed for peak efficiency below maximum power. So you see the efficiency drop off as the power increases. An interesting maybe observation here is that while we don't exceed necessarily the DOE targets for 2020 or 2025, for each individual system, so our inverter is not as powered as the target, or our charger, well, that's competitive with the targets. But once we combine the two, this combined system, we now have only one system that satisfies both roles. And if we accept that as a potential metric, then we can actually show that the combined or the integrated traction drivetrain that charges batteries actually exceeds the DOE metrics for 2025. So that's one note here, both in cost and power density. Maybe the last note on the motor drivetrain is that a common problem in electric motors is the shaft voltages and the resulting bearing current. So the common mode is actually an issue because it tends to shift the voltage of the shaft up and down. And what happens is that this slowly breaks down the isolation in the bearing. There can be small sparks that then destroy the bearing over time. This topology, or stabilizing the common mode, is actually a really good idea because it mitigates most of these shaft voltages. Again, they're decreased by a factor of greater 10. And as a result, you don't need common mitigation strategies for the bearing voltages, bearing currents that otherwise many machines need to implement, and which are brushes or some other strategies. I think I'll stop here for the research. We also do some other related things, or better, we have collaborations where we try to think about vehicle to grid, or leveraging our hardware for vehicle to grid in supply constrained electric systems like New York metropolitan area. Things like demand response or peak shaving have a a very high value because the power system is extremely constrained. Similarly, also the delay of infrastructure investments has a very high value because changing infrastructure in New York at all or in any metropolitan area comes at a very high price. And as a result, I believe there is a potential for electric vehicles, or perhaps more generally for any battery storage, to contribute to the electric vehicles. Another component I didn't talk about, but we do some battery management, both in hardware. This is power electronic hardware that redistributes charge between cells rather than dissipating them, and we can show that this extends battery life by between 15 and 30%, depending on the battery. And then we do some motor estimation. Last thing that I would like to mention is I'm the general chair of ITEC, which is held in Anaheim, California, in June 15 to 17. So I'm afraid the call for papers is already over, but it would be great to see you at ITEC, and if you're interested to come there, please let me know. I'd be happy to show you around. So I think we're at the end of the hour.
Great.
So
Yeah, thank you so much, Matthias. That was a wonderful talk. And I'll stop the recording and we can move on to the question section.